and Atmospheric Sciences Department, IIRS. Today I will be telling you about the retrieval of oceanographic parameters from space. The oceanographic data, which is comprised of physical, chemical and biological parameters. Remote sensing can retrieve the physical parameter like ocean sea surface temperature, ocean currents, and chemical parameters like salinity, color dissolved organic matter, and biological substance, mainly phytoplankton concentration. What can be measured by satellite sensor? These four parameters can be measured by the satellite sensor. First is color of the ocean, it is blue, green or brownish, that can be sensed by visible remote sensing. Then the temperature information can be obtained from the thermal sensors and passive microwave sensors. And the slope and height information can be obtained from the active microwave sensor like altimeter. And the roughness of the sea surface also can be obtained by the synthetic aperture radar, scatterometer, as well as from altimeter data. These four parameters provide a lot of information about the ocean. I will be discussing all these four components with examples. These are the satellite sensors, wavelength range and their utility. First is visible and near infrared sensor, whose wavelength range is 0.4 to 0.8 micrometer, and utility is to retrieve the ocean color and aerosol optical depth over the atmosphere, which is a byproduct. And thermal infrared, which ranges from 3 to 12 micrometer, and it is useful to retrieve the sea surface temperature. And the microwave part, which is in the wavelength range of 0.3 to 30 centimeters, where we are getting sea surface roughness, slope and height information, and other products are atmospheric parameters, which I am not covering. And this is a picture which is you are seeing here. There are blue water, and this is the green water. And, this is the clear water where bottom marks are visible, and here also water. So you are seeing when you are crossing the ocean from open ocean towards the coastal water, the color is changing continuously. That is blueness to greenness. You can visualize when you are crossing you are approaching the shore. So what are the which causes the ocean color to change? Mainly now I will tell you something about the beginning of the ocean color studies. So this is the first paper published in the Proceedings of Royal Society of London in 1922 by Sir C.V. Raman. He published the paper on the molecular scattering of light in water and color of the sea. So there is an interesting aspect of it, that is Lord Rayleigh on ocean color. So Lord Rayleigh is famous for explaining the blue color of the sky. He explained that the blue wavelength is scattered more than other wavelengths. So the air molecules, they scatter blue light compared to scatter blue light more compared to other wavelengths. So sky color what you are seeing is blue. But when he came to interpret the ocean color, he interpreted that the much admired dark blue color of the deep sea has nothing to do with color of the water, but is simply the blue of the sky seen by reflection. But Sir C.V. Raman did not accept above conclusion of Lord Rayleigh, and later explained the blue color of the ocean is due to the scattering of the water molecules itself. So he applied Rayleigh scattering to the water molecules and proved that the blue color is scattered more by the water molecules. So this is the Rayleigh scattering. The forward scattering is equal to the backward scattering. This graph shows you the absorption and scattering coefficient of the water. So what you are seeing here is the red line represents the absorption coefficient of the water. The absorption is minimum in the blue end, and gradually the absorption is increasing towards the red end of the spectrum. In the reverse way, the scattering is more in the blue end of the spectrum, and gradually it is decreasing towards the red end of the spectrum. So if you have a satellite imagery of infrared or red wavelength region, the water will appear as a dark. So this is due to absorption of the sunlight by the water molecules. Now investigators, they have drawn a relationship between absorption, scattering and the reflectance of the water. So reflectance is related to scattering coefficient and absorption ratio by a constant, that is 0.33 BB by A. R is representing the reflectance of the water, and BB represents the back scattering coefficient of the water, and A represents the absorption coefficient of the water. So the reflectance curve is drawn here. So blue water, you will find a high reflection in blue end of the spectrum, and gradually it will decrease. If other substances will present, they will absorb the blue wavelength region, such like phytoplankton, which I will be explaining later on. So the color of the water will change from blue to green. So these are three substances responsible for changing the color of the water. One is phytoplankton, second is suspended sediments, and the third is dissolved organic matter. So these are the phytoplankton species which change the water color. They are of different shapes and sizes, and they are microscopic in nature, and they freely float in the oceanic environment. So phytoplankton is broadly divided into two groups. One is diatoms, then another is dinoflagellates, and this is coccolithophores, and they are covered with calcareous plates, thrive in nutrient-poor waters, means open ocean waters. And these are dinoflagellates. Two flagella thread-like structure are present, and some are responsible for harmful algal bloom, formerly known as red tides. So the red tides, the red tide occur in worldwide, everywhere in the world. So the main is the dinoflagellates, which causes the bloom, and the blooms, when it happens, they release the toxic substances which is hazardous for the marine environment. Both due to their toxicity and abundance, the bloom area is not the forecasting people, those who are forecasting potential fishing zones from using remote sensing data, they advise the fishermen not to go for fishing in the bloom dominated water. Now I will be telling you about the optical properties of phytoplankton. So as you have seen, phytoplanktons are having different size and shape. So they normally come under the mice scattering, and the forward scattering is found to be more than the backward scattering. So this shows you the absorption and scattering coefficient of phytoplankton in the visible wavelength region, and the green line shows you the absorption coefficient of the phytoplankton, and the red line shows you the scattering coefficient of phytoplankton. So you can see the absorption coefficient is prominent in the blue end of the, that is 440 nanometer, and another absorption peak is there here. So if phytoplankton is more in the water, the sunlight will be absorbed in the blue part of the spectrum comparatively. So the blueness of the water will decrease and it will turn into green. So now I will be briefly telling you about the biooptical algorithm development. So in water constituents, that is phytoplankton, colored dissolved organic matter and sediments, they are present in the water, and you have to study the inherent optical properties like absorption and backscattering characteristic of each of the substances, and then you have to model, as I have shown you, R is equal to BB by A, that is 0.3 BB by A. You have to model the reflectance to the absorption and backscattering characteristics, then inverse the model to find out the in water constituents or water quality parameters. So the remote sensing, from the remote sensing data, you will get the radiance or reflectance. Then if you know their characteristic, then you can inverse the model to find out the constituents present in the water. Now, as I told you, in the water, chlorophyll concentration is increasing from 0 level to 5 milligram per meter cube. So 0 means pure water when chlorophyll is not there. So you are getting blue peak in the reflectance, and then as chlorophyll is going on increasing, the reflectance spectra in the blue end is going on decreasing. And you are getting a hinge point at 550 nanometer. So that is a green channel. Suppose you have two bands in a satellite having blue and green, then you can find out the chlorophyll concentration using the radiance or reflectance information from that satellite. So this tells you about the pigment index, that is reflectance at blue wavelength divided by reflectance at green wavelength, that determines the pigment index, and chlorophyll concentration can be related statistically to the pigment index. So it is, I am showing here a simple relationship, A pigment index to the power B, it is in power law, but now sophisticated algorithms are available which takes many wavelengths into account and many logarithmic relationship. I will be telling you about the overview of the ocean color data processing. First we take the satellite data, and then we do the atmospheric correction, and then we retrieve the reflectance or radiance or reflectance of the water. Then whatever algorithm, in situ algorithm which we had developed earlier, that we apply to retrieve the water quality parameters. So the sunlight, which is the source of energy entering into the ocean, and the energy which is leaving the waters is known as water leaving radiance, which carries information about the water quality parameters. So the sunlight is striking at the sea surface, and part of it is getting reflected back, which is known as Fresnel's reflection coefficient rho. So that can be calculated taking the information of incident angle, solar zenith angle, and the refractive index of the water. Then the remaining light which is entering into the ocean water is excessively absorbed and scattered by the water medium. Then the backscattered light is refracted towards the light sensor, which is known as LW, water leaving radiance, which is a important parameter which contains information about the water quality parameters. So we have to retrieve the LW in order to determine the constituents present in the water. So apart from LW, satellite sensor also receives radiance from the atmosphere, which is known as molecular scattering, and the dust particles also present in the atmosphere, which is known as LA, aerosol scattering. So we have to remove LR and LA from the total radiance received at the satellite sensor to obtain the water leaving radiance. This is known as atmospheric correction procedure. So now we have ocean color, ocean in Oceansat 2 we have a sensor, ocean color monitor. We have 8 bands, and the first band is for yellow substance and turbidity determination, and second band for estimation of low chlorophyll concentration, and third is for medium, and fourth is for high chlorophyll waters, and fifth and sixth band are used for suspended sediment concentration and chlorophyll hinge point, and these 7 and 8 bands are used for atmospheric correction of the satellite data. Because water leaving radiance in these 2 bands are negligible and they are considered zero, and whatever radiance received at the satellite sensor in these 2 bands are related to Rayleigh and aerosol scattered radiance. So there are statistical methods which you can use to extrapolate the aerosol scattering in other bands. So this is the basic equation used for atmospheric correction, that is LT is equal to LR plus LA plus LW into T. LT equal to the total radiance received by the sensor, and LR is the radiance due to Rayleigh scattering, LA is the radiance due to aerosol scattering, LW is the water leaving radiance. T is the transmittance of the atmosphere. Once you determine the aerosol optical depth and you know the climatological water vapor concentration or ozone concentration, etc., so you can find out the transmittance of the atmosphere. So while doing the atmospheric correction, taking the radiance from the red and infrared part of the bands, you can estimate and extrapolate the relationship to estimate the aerosol optical thickness in the blue end of the spectrum, blue and green end of the spectrum. Then whole of the satellite data, all 1 to 6, you can all the bands you can do the atmospheric correction accurately. So this is the application of visible remote sensing for monitoring of marine environment, that is seasonal mapping of phytoplankton you can do, and detection and monitoring of phytoplankton bloom you can carry out. Then you can go for quantitative determination of suspended sediments, and ocean coastal circulation and surface currents can be identified using the ocean color data, and transport and fate of the marine pollutants and oil slicks also can be monitored, and assurance studies like coral reefs, bathymetry, etc. Can be carried out using the high resolution data. If hyperspectral data in high resolution is available, it will be nicely utilized to study the coral reef and bathymetry. So this is the phytoplankton bloom as seen by the satellite. It is the sea view image, and this is the Arabian Sea, Gulf of Kutch area, and you are seeing the meanders, and where the means it is associated with certain phytoplankton concentration. So nicely, which is not normally visible in the ocean, means normal imageries. You can find all these fine scale features after doing atmospheric correction and applying the chlorophyll retrieval algorithms, etc. So this is the sea-whips image of phytoplankton. What the dark portion, what you are seeing here, means this is the true color composite image, and the land area is this one, and this is the ocean area. Almost you are seeing nothing here, but after doing atmospheric correction and applying the chlorophyll retrieval algorithm and the pseudo color coding is carried out, you are seeing the fine scale small meanders and small eddies, etc. And the red patches, what you are seeing here, the high concentration of chlorophyll along the coast. It is due to availability of high nutrients in the coastal region compared to the open ocean area. And these are the some of the first Maurice Terra ocean products generated at Satellite Application Center ISRO. And this is the living radiance at 490 nanometer, and this is the chlorophyll concentration image in the Arabian Sea, and it is a byproduct, that is aerosol optical depth of the atmosphere. These three products are highly used by the scientific community. And this shows the ecological impact of algal bloom, which is responsible for messy fish kills and harmful to birds and manates. So earlier what I had told you, that the agencies which are forecasting potential fishing zone to fishermen community, they alert seeing the satellite data the probable bloom areas to the fishermen, and they advise them not to go for fishing to those areas. And this picture shows you the high concentration, low concentration of chlorophyll around 0.48 milligram of meter cube, and this is the remote sensing reflectance, and it is blue water. Then when chlorophyll concentration is increasing, that is green, represented by green and red, you are seeing the blueness has decreased and it has changed. Now it is peaking in the red end of the spectrum. Now you can take the wavelength around this and this. In one study they have taken these two wavelengths. You can take other wavelengths also, and you can determine the chlorophyll concentration which is in a logarithmic way. So chlorophyll A is some constant exponent to the power, the ratio of the two channels will give you information about the chlorophyll concentration. So those areas can be easily detected by the satellite sensor, particularly in the red band. You can find out the red and infrared band, you can find out the algal blooms. And this one picture shows you the trichodesmium bloom observed in the Saurashtra coast during month of May. So this is carried out by IRS P4 OceanSat-1 sensor, IRS P4 Ocean sensor in OceanSat-1, and this is the picture of phytoplankton age observed by MODIS. I had some animation for you, but unfortunately the software is not supporting the animation. Otherwise you would have seen the finer pictures and the plumes, etc. And this is this shows you the progress of the means increase of productivity in the water as well as over the land. This is the situation in March where sun is near the equator, and as sun is moving towards the North Pole, that is in April, the greenness in the water in the northern hemisphere is changing, and May it is totally increasing. So it is it is getting more sunlight in these months. So greenness in the water, that is primary productivity in the water, and the land productivity also increases. And this also was the animation of 10 years data, but the animation is not working. So you would have seen there how the chlorophyll and the vegetation in the land is changing with the seasons. Now I will tell you about the remote sensing of coastal waters. What I told you about retrieval of chlorophyll in normally it is without any difficulty in the open ocean water or the K1 waters where the turbidity is very less. But when you are entering into the coastal waters, many factors are affecting the optical properties of the water. So it is called optically complex water, coastal waters, and they come under case 2 waters. So the apart from the chlorophyll, apart from the phytoplankton, upwelling radiance is comprised of radiance coming from the phytoplankton, then water molecules, then dissolved organic matter, and the bottom and suspended sediments, and the bottom vegetation, etc. If seagrass is there, those things will also contribute to the upwelling radiance. So to separate individual parameters in the optically complex water is bit difficult. So I am showing here the absorption and backscattering coefficient of suspended sediments. Normally there is a U-shaped absorption coefficient, and the scattering coefficient is convex one. And but this is a site-specific spectra that is pertaining to the east coast of India. But you will get other spectra, means need not be U-shaped, it may be exponentially decreasing also. So this absorption and backscattering spectra you can use in the model to retrieve the reflectance of the water with varying suspended sediment concentration. So you can see that as suspended sediment concentration is increasing, the reflectance spectra almost in all the bands they are increasing. So you can take one particular band or combination of many bands to retrieve the suspended sediment concentration. So one such exercise we had taken to retrieve the suspended sediment concentration using IRS-1 sweeps data, where we have taken the red band into consideration, which is showing a linear relationship as the suspended sediment concentration is increasing, the reflectance is also increasing in a linear way. But as the wavelength is going to shorter one, means smaller wavelength region, that is red to green, then it is becoming, the relationship is becoming non-linear. So you have to take which waveband you are taking. So this is the suspended sediment concentration retrieved using IRS-1 sweeps data. This is the east of India, that is Paradip port is here, and Mahanadi river is pouring a lot of suspended sediment coast. So it is visible here. So we have carried out a sea truth campaign using the taking the opportunity of synchronous satellite paths, and we have collected many points. But due to cloud cover, we could only match few points where we are getting similar a linear relationship. So you can use this data, develop algorithm, and monitor the suspended sediment concentration. This is the suspended sediment concentration is seen by the sea whips data in different coastal area of the world. And this is the coastal circulation and plume dynamics using ocean sediment images in Krishna Godavari Delta, Bay of Bengal. This study is carried out at SAC Ahmedabad, and the wind vectors are plotted using QuickSCAD data of NASA. So you can see here as the wind is coming from the northeast direction and towards south, and the wind generated ocean currents the pushes the sediment plume along the wind direction southward. And here the trend is reverse, and some other season, and the wind is going towards the northeast direction, and the currents are also getting pushed towards north. But here you can see the ocean dynamics, and some plume has come into the middle of the way. So deviating instead of going towards north. So this type of small scale features you can detect from the satellite data. Later on you can find out the dynamics involved in it. So these are the patterns of suspended sediment showing large scale sediment transport and circulation features along parts of Indian coast using the OceanSat-1 OCM data. So you can see the suspended sediment concentration is not only confined to the coastal area alone, but it has gone deep into the middle of the bay. So many instances are. Now I will come to cover the thermal remote sensing. The thermal infrared remote sensing, which is based on the Planck's law, and the whatever body which is having a temperature, they will radiate the radiation, and if you have a thermal sensor, the radiation is captured here, and when you will apply this equation, you can invert this equation, you can find out the temperature T. So means using the thermal bands. There are many thermal bands in many satellites, and this principle is used to get the temperature of the object. Whether it is water or land, it is depending on the emissivity factor, so you can get the temperature of the object. So I am giving you the characteristic of NOAA AVHRR channel, advanced very high resolution radiometer, which is normally is having 5 bands operating in visible and near infrared, and then reflective infrared, and 2 bands are in thermal infrared. So they give you 1 kilometer by 1 kilometer resolution sea surface temperature, and swath width is around 2580 kilometers, and hook angle is 55.4 degrees. So this NOAA AVHRR sea surface temperature data is used frequently by the scientific community to interpret the sea surface temperature. Apart from that, other satellite sensors are there which can give you the sea surface temperature. So this is the summary of application of thermal remote sensing for monitoring marine environment. You can study the climatology and the trend in the global change in SST, and short-term weather prediction, and gas exchange across the air-sea interface, that if the temperature is getting cooled, the absorption of gases will become more, and those things you can study. And dynamical oceanography, you can see the warm currents, cold currents, etc. And where upwelling is occurring, those features you can identify easily using the thermal sensor data. And the pollution studies also can be carried out if you have a high resolution sensor. So this is the sea surface temperature from the Kalpana-1 satellite, and this is the MODIS Terra, which is giving same day the sea surface temperature. So we have carried out a comparative study. Both are giving nearly exact temperature. Then this is the Modis Equa data, and this is Kalpana data for another time. And this is the sea surface temperature from the advanced microwave scanning radiometer AMSRE in the Equa satellite. So the advantage of microwave sensor is it can penetrate through clouds, and it can give the sea surface temperature information in presence of clouds also, but it fails, means the thermal sensor cannot give you the sea surface temperature when clouds are present. So taking this advantage, these microwave sensors give us a lot more information, means global scale sea surface temperature information compared to thermal data. This is SST from Modis. This is high resolution data, but as I told you, animation is missing here. Now, these informations are available in the MOSDAC website. A lot of the satellite data products, what I showed you about the Kalpana data, INSAT data, and Oceansat 2 data, those are available in the MOSDAC website. One can go for retrieval of those data for their scientific investigation. And one of the application for PFZ identification, we take sea surface temperature data and chlorophyll data from Oceansat 2 and Modis, and we can overlay and do the, you can carry out the GIS analysis, find out the frontal region, EDs and meanders, etc. And you can identify the potential fishing zones and inform to the fisherman community. This is carried out mainly by INCOIS, and this is the PFZ mission. The mission is to make the potential fishing zone advisories as part of the value chain of fishing community, and the R&D effort and modeling technology developed by the scientific community will go for a operational generation of PFZ maps from remote sensing products like SST, chlorophyll, and wind speed, etc. Except during the fishing ban periods, of course, and dissemination in the process of multilingual delivery, map, text, fax, phone, newspaper, internet, email, and electronic display boards, radio and TV broadcast information centers. And finally, the fisherman, this information reaches to fisherman, and the fisherman community, the cooperative societies, etc. They give feedback for the validation. So the user awareness program carries a lot of weightage here. And this is the Indian National Center for Ocean Information Services, which carry out the potential fishing zone forecasting activity. Apart from many other forecasts also being carried out from the center. Now I will go to tell you about the active microwave remote sensing of the sea. First of all, the altimeter, which is most important for oceanographers. This satellite, I had an animation, but it again stopped. So it sends a pulse to the ocean floor and measures a written pulse. The time difference tells you about the height of the satellite from the ocean surface. So if two heights are known, the slope of the ocean surface will be known. Apart from that, it gets the roughness of the sea surface, and the waveform analysis gives you the information about the significant wave height retrieval. So these are the parameters retrieved from the using the altimeter. One is sea surface height, what I told you earlier. Then significant wave height from the shape of the written waveform, and the wind speed. So significant wave height is estimated from the change in the slope of the leading edge, and the power of return signal is related to the wind-induced roughness of the sea surface. So this is the bottom of the ocean, and this is the geoid of the ocean. Then this is the sea surface. So the height is measured by the satellite altimeter, and the ellipsoid, this orbital height is known, referred to the ellipsoid, and the geoid height, if it is known, then you can get the zeta, the deviation of the sea surface above the geoid. So H is the satellite height above the sea, eta is the sea level elevation above the geoid, H is the geoid elevation above the center of the mass, alpha is the slope of the current. So if you get the slope, you can find out the, if you get the zeta, you can find out the slope current. So you can find out geostrophic current from the information, because water will flow from higher pressure to lower pressure area, and due to Coriolis force they will deflect towards the right in the northern hemisphere. This is the geostrophic current you can get from the satellite altimeter data. And basic principle of altimetry is when a pulse is sent to the surface of the ocean, it will get reflected back to the sensor at difference. Then you will get a, if the surface is very flat in nature, there is no disturbance, you will get a shape like this, and this will be the leading edge, and this is the flat plate you will get here, and for a smooth surface. But if the surface will be rough, then the flatness will not be there, and there will be a shape. So in practice, sea surface is rough rather than flat. As a result, the first reflection of the energy commences when the leading edge of the pulse reaches the topmost crest of the wave earlier than the flat surface. But the reflected energy does not achieve maximum until the trailing edge reaches the lowest wave trough. In this way, the altimeter able to average out the effect of ocean waves. This parameter is called significant wave height. This is the principle used to find out the significant wave height. So you will get different slopes in the leading edge, which will give you information about the significant wave height. So this is actually a single echo, how it looks like, and then if you are averaging 25 echoes, you will get a better shape, and 1000 echoes, you will get a nice shape. So normally this type of shapes are more applicable. So as a result of random distribution of the ocean wave facet at any instance, each individual return signal is very noisy, but averaging many successive pulses can reduce this. So using this principle, you can you are seeing here for different significant heights, starting from 2.75 meter to 9.29 meter, you are getting the leading edge slopes are different. So based on this, you can find out the significant wave height of the ocean. Then we had Topex Poseidon is a result of satellite which carried the altimeter sensor. Topex Poseidon is a result of cooperation between NASA, National Aeronautic and Space Administration, and CNES, that is Space Agency. Topex Poseidon is based on 3 earlier Earth orbiting satellite missions, that is GOES-3, CSAT and GeoSat. And it started in 1975, which gave a precision of 20 centimeter and accuracy of 50 centimeters. Then CSAT was still better than the GeoSat-3, and but CSAT lived for 100 days only. So after that, GeoSat in 1985, same as CSAT efficiency. And in addition to Topex Poseidon satellite in December 2001, JASON, another satellite with radar altimeter was launched. JASON 1 is much smaller to Topex Poseidon. All other characteristics of one are similar to Tropics Poseidon satellite. Now we have Saral Altica with us. The Saral Altica project is a collaboration between France and India in the environment monitoring domain. Altica is an innovative car-band altimeter system dedicated to accurate measurement of ocean surface topography. So the car-band is free of ionospheric effect. Normally, the ionosphere attenuation creates a problem for other bands. So car band is used for that, and it is the footprint of Saral Altica is very highly used for coastal altimetric study, and this is the sea level height information derived from the Jackson 1 altimeter, and this is the sea surface height anomaly from Altica, and this data is available in Mostat website. One can download the data, which is free of cost. Then this picture shows you the reflection of incident radar beam. If the sea surface is very calm, then if radar beam is coming, and it will get reflected in the opposite direction, and very less amount of backscattering will be there. So the radar image will look very dark in nature. But if the sea surface is a little bit rough, then some amount of backscattered energy will come back to the radar antenna. So it will increase the brightness of the image. And if totally rough, the isotropic scattering will occur in all the directions. Then if there is a building, you will get a corner reflection. These are the principles of, if you are getting a corner reflection, which will be very bright in nature, and those building points will be used as a reference points for geometric correction, etc. Now, if two objects are there, one is house here, another tree here, I had animation again, it is not visible. So now first written will be from the house, and second written will be from the tree. This distance, the time difference of the written pulse, written backscattered signal will give you between two objects on the ground. This is the principle used to image the ground objects in the radar, and this shows you the OceanSat 2 scatterometer, which operates which scans the ocean surface to get the backscattered energy, which can be related later to the wind speed of the over the ocean. And the inner beam, there is an outer beam and there is an inner beam. The outer beam is vertically polarized, inner beam is horizontally polarized. You can correct it here. It is V is the outer beam and H is the inner beam. So these two beams are used to retrieve the wind speed over the ocean, and this is the vertically polarized backscattered power, and for different wind speeds it is giving different amount of backscattered energy, and it is in the azimuthal direction also the trend is different. So you can use the retrieval procedure utilizes the geophysical algorithm taking the backscattered energy, and there is a process to find out the wind vectors, and this image shows you the scatterometer products in the recent two cyclones, that is the wind speed over the ocean, and this is Shandy, 29th October, and Neelam about 31st October. This is the wind speed and wind vector vector over the ocean derived from postcard data. And this is the data means wind speed and wind vector data available in the website of National Remote Sensing Center. So Hyderabad, you can register yourself and download the data for further analysis. And then I will be telling you about the monitoring of nearshore coastal bathymetry using remote sensing tools, using all the sensor data mainly. And these are the bathymetric chart which is useful for construction of oil, pipeline and cable companies, harbor and shipping control authorities, resource mapping agencies, coastal protectors, etc. So nearshore bathymetry can be monitored from the following remote sensing sensors using visible remote sensing, LiDAR and SAR. Visible remote sensing, here you can use the regression analysis and optical model. In regression analysis, the satellite DN count or reflectance or radiance can be used with the in situ observed depth, and both should be synchronous, means satellite pass and in situ observation should be synchronous with each other to get a better result. And you can develop a regression equation and directly you can convert the satellite data into the bathymetry. The optical method model, the reflected light from the ocean bottom gives information about the depth of the water provided the following parameters are known, that is absorption coefficient of the water and bottom reflectance of the water. If these two parameters are known, then you can go for retrieval of depth of the ocean. That is the solar light is reaching here, and if you know attenuation coefficient of the water, how much light it is getting reduced here, you will know. Then if you know the bottom reflectance, bottom material, that is sand, silt, clay, if their reflectance property is known, then how much light reflected back you will know. Then water leaving radiance reaching at the satellite sensor you will know. So inverting those things, you can find out the depth Z of the water. This is an analytical model, but these two parameters will not, means this method will not work in highly turbid water. It will work in clear to moderately turbid water, where the light should touch the ocean bottom. And this is the bathymetry from the remote sensing data, that is regression using the regression model. One is spot data, another is TM data. Different colors show you different depth counters. And this is the high resolution data, some study carried out in the waters of Minicoy Island, and some we have classified the data for a GIS analysis to find out suitable site for pearl culture. And this is the use of bottom reflectance image for classifying remote sensing images, that is classified map using IRS-1C list data, band 3, 4, band 2, 3, 4 without any correction. Now we have classified the map using the water leaving radiance image and the bottom reflectance image, two images. You can see the variation. And these are the field operations carried out in the Andaman Seas to map the coral underwater coral reefs using the TM data. And these are some of the map of coral reefs around the Andaman Islands. So limitation of visible remote sensing for bathymetric studies, bathymetry up to 30 meters can be surveyed using this method, and the accuracy depends on water quality and substrate type. And bathymetry could not be retrieved from high turbid water because the incident light gets absorbed before getting reflected from the ocean bottom. And a non-uniformity in the water turbidity and bottom reflectance cause additional complexity with the technique. Now LiDAR, So LiDAR, light detection and ranging, is an optical remote sensing technology that measures the property of the scattered light to find the range or other information of a distant target. Of course, this instrument is placed on the aircraft. So the delta Z can be found out. This is the speed of the light, and time difference divided 2 gives you the distance. So what can be measured? That is water depth from sea bottom reflection. Second one, substances at the water surface and underwater from the backscatter and fluorescence information. So you have a green band and a infrared band here. So the light, laser light. So one penetrates the water, one is getting reflected from the water. The difference will give you the water depth. That is the IR laser pulse is around 1064 nanometer, and the green pulse is around 532 nanometer, and so these two differences will give you the water depth. So the surface, this graph shows you the surface written, the bottom written, and the signal from the water column. So this is the some survey carried out. It is in some foreign soil. So this is the surveying for underwater pinnacles. This is the area, and this is the two-dimensional image. And after laser scanning, you can get this type of information. And this is the sunken cargo vessel below the sea surface in the Baltic Sea. Water depth is 25 meters. And this is the channel channel through a coral reef. And these are the bathymetrical radar performance. Maximum depth you can go up to 60 meters. Operating altitude is 400 meters, and scan width is 220 meters. These are the challenges, that is small object detection, identification, etc., seafloor classification, and land water discrimination, and these are taken from this website. You can get a lot more information. And the synthetic aperture radar, now it is operating in many modes. The aperture of radar is actually extended to allow for more data collection at variety of resolutions and swath sizes. So the advantage of utilizing SAR data, that is SAR data can be used in regions such as estuaries where survey ships could experience difficulties. The survey can therefore be completed at a reduced level of risk to equipment crew. Frequent revisiting cycle of SAR allows the regular updating of maps of areas where bathymetry is prone to rapid changes such as shipping channels subject to strong sediment, etc. So the principle is the variation in water depth, pressure, tide generated currents, and those perturbation can propagate upward to modulate the pattern of the sea surface roughness. So where there is a ocean bottom is interfering with the motion of the water above, there will be a compression and rarefaction, etc. So where it is compressed, the sea surface will be rough, and the backscattering will be more. Then in the radar image you will get a white page. So dark and white pages will give you information about the wave wave modulation near the coastal area. That is, if the wind speed between 3 to 9 meter and the magnitude of the tidal current is sufficiently large, that is 0.5 meter per second, then the surface modulation can affect the backscatter observed in SAR image of the region, allowing the observation of certain bathymetric features. So what you can do, you have to use a hydrodynamic model, that is bathymetry assessment system, which consists of a suite of numerical model which calculates which simulates a synthetic SAR image first burst bathymetry, the difference between the synthetic image and the actual image is minimized, so that to generate a update bathymetry. This process is repeated until the depth values converge. So this is the application. This is the SAR image. Where there is backscattering is less, you are getting the darker page. Where backscattering is more, you are getting the white tones. So now after applying, you are getting the bathymetric information. Then this information also you can use retrieval ocean wave spectra from SAR image. Some typographical error here. So the wave period and the is associated with certain relative energy. So similarly, this shows the principle is the simulated image of a sinusoidal wave. This type of images can be achieved by the from the SAR image, and later on it can be converted to corresponding wave spectrum. So the image and the wavelength is 120 meters, and the direction is 45 degree. So you can see the corresponding wave spectrum. So similarly, this way NVSAT SR wave data, which is acquired 5 kilometer by 5 kilometer resolution. This is the path, and this is the one portion of the image, and the corresponding wave spectra. This can be used in the models. Then the ocean salinity from SMOS, that is European Space Agency Soil Moisture and Ocean Salinity satellite. They have launched the satellite in November 2009, and it is designed to give the soil moisture information and ocean salinity information. This is the one of the initial products. And this is the principle, that is 1.43 gigahertz. For different sea surface temperature, and different salinities, the brightness temperature received at the sensor will be can be mapped out from this. And this is the another waveband at 2.85 gigahertz, but the salinity information is suitably extracted using 1.43 gigahertz. So this is the salinity information from conventional measurements, and this is the information retrieved using the satellite measurements. So the another satellite Aquarius, this also uses the same principle, and that is 1.43 gigahertz sensor to retrieve the sea surface salinity, which is a very useful parameter for studying the ocean dynamics. And some of the applications I am going towards with atmosphere, and this is the satellite data which provides information about the cyclones, and the radar data, radar images provide all the same way provides the information about the cyclones. This is the RadarSat-2 data and the ReSat-1 data, and after just before the landfall and after the landfall, how the water is inundated in the coastal area, and how the it is another image. It is a forest, and this is how the water has entered into the city, and captured by the satellite data and high resolution satellite data, how the city area is inundated with water. And this is cyclone is approaching to the coast, and this is the radar image before the cyclone approached the coast, and now as the cyclone is approaching the coast, you can see the water has entered into the coast. These are storm surge waters captured by the radar image. So this can be this is nicely captured here. So storm surge phenomena due to the low pressure of the cyclone, as well as due to the tidal elevation and wind setup, wave setup near the coast. And yeah, you can see here the progress of the cyclone. This is the eye of the cyclone, along with the storm surge water is progressing toward the coast. And Megatropic is an Indo-French joint satellite mission for studying the water cycle and energy exchange in tropics. The main objective of this mission is to understand the life cycle of convective systems that influence the tropical weather and climate and their role in associated energy and moisture budget of the atmosphere in tropical regions. So these are the instruments present, Madrasa, Saphir, and Scarab, etc. So these are two products you are getting. One is providing you a long wave flux at the top of the atmosphere, and the short wave flux at the top of the atmosphere. These are the important parameters to study the oceanic heat budget study. Thank you.